Alright, so I'm going to show you how to work out these momentum problems. The formula for momentum is P is equal to M times V. P is momentum, M is mass, and V is velocity. Remember, that's the very same thing as speed. Those two can be used interchangeably. Alright, so if we look at this little pyramid thing that I showed you last week, this is a three-part equation. P is M times V. So, P is M times V, or V is P over M, or M is P over V. So we look at the first one. A pitcher in a professional baseball game throws a fastball, giving the baseball a momentum of 5.83 kilograms meters second. Given that the baseball has a mass of 0.145 kilograms, what is its speed? So we're solving for velocity. That's just momentum divided by speed, or divided by mass. So we're going to take the 5.83 kilograms times meters per second and divide it by 0.145. So 5.83 divided by 0.145 is going to be 40.21. And we are solving for velocity, so the units for that is just going to be the meters per second. If we look at number 2, the maximum speed measured for a golf ball is 273 kilometers per hour. If a golf ball with a mass of 47 grams has a momentum of 5.83 kilograms times meters per second, the same as the baseball in the previous problem, what would its speed be? How does the speed compare to the golf ball's maximum speed measure? So we're solving for speed. And we're not going to do this last part. Alright, so if we're solving for speed, that's going to be V is equal to P divided by M. So the momentum is the 5.83. And then the mass is 47 grams. But notice that the momentum is in kilograms. So if we take 47 grams and change it to kilograms, we're going to have to move the decimal back 1, 2, 3. I showed you last week the KHDUDCM. Grams is just a base unit, so we'd move it over 1, 2, 3 to get to kilograms. So we're going to divide that by 0.047. So make sure that you always check your units. So that's going to give us 124, and we're solving for speed, so that's going to be meters per second. We're not going to do number 3, so we're going to move on to number 4. The lightest pilot-driven airplane ever built was the Baby Bird. Suppose the Baby Bird moves along the ground without a pilot at a speed of 88 kilometers per hour. Under these circumstances, the momentum of the empty plane would be only 2,790 kilograms times meters per second. What is the mass of the plane? So we're solving for mass. So mass is going to be equal to momentum divided by velocity. So the momentum we said was 2,790, and that's kilograms meters per second. And then the velocity is 88 kilometers per hour. Notice that the two do not match up. So I'm just going to go ahead and give you this in meters per second. So let's just do this as 24.44 meters per second. All right, so let's go ahead and divide that by 24.44. So 2,790 divided by 24.44 is going to be 114. And that is mass, so that will be, let's Let's move along to number 5. The most massive automobile to have been manufactured on a regular basis was the Russian-made ZIL 41047. If one of those cars were to move at just 8.9 meters per second, its momentum would be 2.67 times 10 to the 4th kilograms meters per second. Use this information to calculate the mass. Alright, so we've already said that mass is equal to momentum divided by velocity. So the momentum of this is 2.67 times 10 to the 4th. And we're going to divide that by the velocity, which is 8.9 meters per second. Okay, so if something's in scientific notation, I told you this last week, but make sure that you put it in parentheses and then do whatever else you need to do. So that's going to come out to be 3,000, and it's mass, and the mass we were using was kilograms. Okay, number 6. The brightest, hottest, and most massive stars are the brilliant blue stars designated as spectral class 0. As is the case of all stars, class 0 stars move with speeds that are measured in kilometers per second. If a class 0 star moves with a speed of 255 kilometers per second and has a momentum of 8.62 times 10 to the 36 kilograms meters per second, what's the star's mass? So solving for mass, that is momentum divided by velocity. Alright, so the momentum is 8.62 times 10 to the 36th. That's kilograms per meters per second. And we're going to divide that by the velocity. Notice this velocity is in kilometers per second, but we have the momentum with meters per second in it. So we're going to convert that. So if we go from 255 kilometers to meters, we're going to have to move the decimal over 1, 2, 3 to the right. So that'll be 255. And I just used that KHDUDCM to convert that. We were at kilometers and we wanted to go to meters. Alright, so we're going to plug this in. This one's in scientific notation. Make sure that you put it in parentheses. And then we're going to divide that by 255,000. So that comes out to be 3.38 times 10 to the 31 power. Notice at the end of this out here, it's got that E31. That's the exponent. It's in scientific notation, so it'll be 10 raised to whatever that is after the E. We're not going to do part B. Okay, number 7. The 300 series Shinkansen trains consist of 16 aluminum cars with a combined mass of 7.10 times 10 to the 5th kilograms. The reduction in mass from the 100 series enables the 300 series trains to reach a top speed of 270 kilometers per hour. What is the momentum of one of these trains at its top speed? And we're just going to solve the problem. We're not going to do all the comparison stuff, so we're not doing this part. So we're looking for momentum. So P is equal to M times V. So the mass of the train is 7.10 times 10 to the 5th kilograms. And then we're going to multiply that by the speed, which is 270 kilometers per hour. So we're going to plug that in. 7.10 times 10 raised to the 5th times 270 comes out to be 1917, and then it's got 1, 2, 3, 4, 5 zeros. So we're going to put this in scientific notation. So we're going to move this over 1, 2, 3, 4, 5, 6, 7, 8. You want one digit in front of the decimal. So that's 1.917 times 10 to the 8th. All right, the largest animal to have ever lived on Earth is a blue whale. Consider a blue whale with a mass of 1.46 times 10 to the 5th kilograms and at a top swimming speed of 24 kilometers per hour. What is the momentum of the whale at this speed? So momentum is mass times velocity. So the mass of the whale is 1.46 times 10 to the 5th. The velocity is 24 kilometers per hour, so we're going to plug that in. 1.46 times 10 raised to the 5th times 24. That comes out to be 35040. We're going to move this into scientific notation, move it over 1, 2, 3, 4, 5, 6. So it'll be 3.504 times 10 to the 6th. Okay, 9. In 1996, Michael Johnson ran a 200 meter in 19.32 seconds. Johnson's mass at the time of his record-breaking run was about 77 kilograms. What is his momentum at his average speed? So we know that momentum is mass times velocity. We've been given the mass, and we've been given what we can do, what we need to find the velocity. Remember, speed or velocity is just distance over time. So his distance was 200 meters, and his time was 19.32 seconds. So we got to find the speed first. So 200 divided by 19.32 is 10.35, and that's meters per second. We measured that in. So now we're going to take the mass, which was 77, multiply it by that 10.35 that we just found. So his momentum was 797 kilograms times meters per second. Okay, so now you're going to work on the mixed practice on your own. If you look at number 10, it asks for what was the speed in meters per second and kilometers per hour. You're just doing meters per second, so do not do kilometers per hour. So it gives you a momentum, and it gives you a mass, solving for speed. And the next one, you're solving for mass. It gives you a momentum, and it gives you a speed. 12 is one that you're going to have to calculate the speed on. So remember that speed is distance over time. So you're going to have to take his distance, which is 274, divide it by the time, which was 8.65. So that will give you your velocity or speed that you can use. And then there's the mass to find the momentum. $13 is asking for speed. It says in both meters per second and kilometers per hour, but we're not doing the kilometers per hour. Just find it in meters per second. 14 is asking for mass. I went ahead and converted 96 kilometers per hour into meters per second for you, so you didn't have to do that because your momentum's got meters per second in it. So it's 26.67 meters per second. 15, you're solving for momentum. So it gives you a mass, it gives you a speed, and we're not doing this part here. How does it compare? Just mark that out. 16, you're solving for speed. We're skipping 17, and then 18, you're solving for speed. So you need to make sure that you take notes on what I went over with you, turn that in, and then solve the mixed practice, and take a picture of that, and turn that in as well.